We're going to continue our conversation about commercial refrigeration by talking about some of the additional components you find on most commercial refrigeration systems. Now, you're not going to find each one of these on every system, but as you go through your career, you're going to find different combination of these depending on the application and, quite honestly, who installed the system. So let's start off with the four basic components, just so we know what the standard is. Okay, we always have to have a compressor, condenser, an expansion device, and an evaporator. Some of this is review. We have other components that enhance system operation, and these controls can be electrical, mechanical, or electromechanical devices, which is a combination of two. The mechanical controls start, stop, or modulate fluid flow to increase system effectiveness. So we have sometimes we have two temperature controls, okay? Which is two temperature evaporation. Operation is utilized when there's multiple evaporators in a system. Think about a grocery store. You have a line of freezers, okay? You have a line of possibly a freezer and a refrigerator or a cooler. These are two different temperature operations because you may not want to keep everything at 0 degrees. You might want to have some product at 29 degrees to be set for food storage purposes. So the pressures in these evaporators are therefore different. Two temperature operation is normally accomplished with mechanical valves. Okay, here's an example of it. If you take a look at the top evaporator, it's at 20 degrees. The bottom evaporator is taken at 30 degrees. So we have 26.1 psi and 18.4. We know that there's a temperature pressure relationship between refrigerant and the outside temperatures. So what we use is called an evaporator pressure control, or EPR, evaporator pressure regulator. It prevents the pressure in an evaporator from dropping below a predetermined value. We're not saying, okay, we're going to make sure that one goes lower. We're basically saying that this control will prevent the higher temperature evaporator from dropping below where we want the set point. There's two pressures that control these valves. One is spring pressure. It pushes to close the valve. The other is the evaporator pressure, which pushes to open the valve. Okay, the evaporator superheat may be high when the EPR is closed. Here's an example of an EPR. Okay, so again, we have the spring over here. This is the portion you can set by turning the knob. There's a seat disc and a seat. The vapor from the evaporator pushes up on the spring pressure and sends vapor back to the compressor. Now, there's one thing you have to be very careful of when you're using an EPR or diagnosing an EPR system. You have to take your superheat readings before the EPR. If you take your superheat readings over at the compressor, you're going to find out your system superheat may be in the 60s or higher. So you have to take your superheat readings at the EPR. An EPR is needed in the suction line of each evaporator except for the lowest temperature coil. Okay, so if you have 4 evaporators, you have to pick one which is the lowest temperature and not put the EPR in that. EPR valves are equipped with a Schrader valve to read evaporator pressure. Multiple EPRs can be set to different pressures, so each evaporator is maintained at a different temperature. So again, just be very, very careful on superheat when you're dealing with EPRs. Also, if you adjust an EPR, you have to retake the superheat of every other evaporator that's on that system. Because once you change pressures on one, it has the capability of actually affecting every other evaporator. So here's another example, okay? We have 3 evaporators. One is set for 28 psi, one is 18.4, one is 10 psi. So that's going to be your lowest pressure evaporator. Notice there's only 2 EPR valves. The center one, which is my lowest temperature, does not have an EPR valve. It has a direct route back through my suction line to the compressor. Okay. We sometimes see electric evaporator pressure regulators, or EEPR valves. They are much more accurate. They're located at the evaporator outlet, and they can be used on single or multiple evaporator systems. In this case, microprocessors sense the discharge air temperature. So before, when we're talking on this one, we're talking pressures. When we're talking about electric evaporator pressure control valves, we're talking about discharge air temperature. They're designed to maintain discharge air temperature in the refrigerated motor, in the refrigerated case. They're controlled by a bipolar step motor. Okay, so in other words, they open in steps. Okay, it's sort of like a stair step. If the temperature's rising a little bit too high on the discharge air temperature, it will take one step up and open the valve a little bit. Then it will reevaluate itself with the CPU or the control module itself, and it will say, okay, did my discharge air temperature come down to the temperature we want it to? If it did, it will stay where it's at. If it hasn't come down, it will do another step. So these are relatively medium speed acting, but they are very accurate, and they provide a lot of energy efficiency. Our next device we're going to talk about is a crankcase pressure regulator. Okay, it's located close to the compressor, and it prevents the compressor from overloading on startup. It provides a limit as to the pressure that can enter the compressor. It's also sometimes referred to as a close-on-rise of outlet valve. It resembles an EPR valve, and again, it's on the suction line very close to the compressor. And if you have a very hot case, in other words, it's been open for a while, it's been shut down, or a lot of new product is in the case that needs to be brought down to temperature, it will prevent the compressor from getting that high pressure suction as the system starts up. Okay, the crankcase pressure regulator, again, it looks very much like the EPR. We have our vapor from the evaporator. We have a Schrader valve for checking the actual evaporator pressures, because if you check at the compressor on this, you're again going to get superheats that don't make sense. We have a spring valve, okay, and we have the vapor to the compressor. And here's an example of how it would be installed in the system. So if we have an evaporator that's actually higher than the temperature we want it, and if we only want 5 psi at the max going to the compressor, in other words, this is a low temperature system. The compressor can't handle more than 5 psi. We put in a crankcase pressure regulator that prevents that system from giving the full pressure to that compressor. These are used in low temperature applications, like deep freezes where our normal evaporator temperature is -20 degrees. Okay, to adjust this valve, we adjust it under a high load condition. In other words, not normal operating conditions. In other words, we want our case higher than normal. We want to put an ammeter onto the compressor circuit when we're setting the valves. We do not want to have excessive amperage. Okay, if the amperage is higher than normal, we need to turn the adjustment screw into the valve to reduce the refrigerant pressure returning to the compressor. Turning the screw out of the valve increases the refrigerant pressure returning to the compressor. So again, higher amperage, close it down. Too low amperage, open it up. We do want the most possible refrigerant coming back to the compressor. We don't want to restrict it too much because the refrigerant is what cools the compressor. But we want to prevent high amperage because high amperage will actually damage the compressor. In a lot of large systems and in a lot of systems that are enclosed in areas, we're required to have relief valves. Okay, what they do is they release refrigerant from a system when a high pressure condition exists. We have some that are spring loaded. They're located in the vapor space and they reset after opening. Some of these are internal of the compressor as well. Then we have the one-time type. Okay, it's fitted with a low temperature solder, and it's normally located in the suction line near the compressor. This is an example of the spring-loaded type. Okay, this is the valve in the closed position, and if the pressures get too high, it will push the valve open and allow refrigerant to escape. Okay, so again, now the valve has been pushed open because of the high pressure, the red refrigerant, it allows refrigerant to escape. This is a one-time relief valve. It's like an oil plug in an oil pan of a car, except it has a hole in the center of it that's filled with a low-temperature solder. If that refrigerant gets too hot, it's going to melt the solder, and it's going to allow the refrigerant to escape. Now, this one will not reset, and it will empty the entire system. Anytime we have a relief valve open, we need to go back and find out why. Relief valves are the last protection it has before we could take a stance of starting to pop lines apart based on high pressure. Our next control is the low ambient control. You see these a lot around New England, especially on condensers that are mounted on the roofs. Okay, roofs of restaurants, grocery stores, and other buildings that have refrigeration systems. Starting to see them quite frequently also on air conditioning systems that are used year-round. What they do is they're also known as fan cycling, fan speed, air volumes, or condenser flooding controls. They're intended to simulate design operating conditions. They keep the system's operating pressures within desired ranges. The device opens on a drop in head pressure. Okay, if the high pressure drops too low, it's going to open a switch and turn the condenser fan off. As the head pressure, the high pressure rises, it closes, turning the condenser fan back on. The fan cycling will cause large variances in the head pressures, and they're best used on systems with multiple fans. That's the fan cycling head pressure control. Fan speed control works almost the same way, except it keeps the head pressure a little bit more stable. As the outside temperature drops, the fan slows down to reduce the amount of airflow through the condenser coil. As the outside temperature rises, the fan starts to speed up, increasing the airflow through the condenser. Some of these controls monitor the refrigerant's condensing temperatures, and some are again based on pressures. There's one more control, actually two more, but the next one that's used is called an air volume control. You see these on large rooftop units. It utilizes piston control shutters or dampers. As the head pressure drops, the shutters close, reducing airflow through the condenser. The reduced airflow causes the head pressure to rise. During periods of warm ambient temperatures, in other words, high outside air temperatures, the dampers are fully open to allow as much airflow as possible through the condenser coil. Remember, as we talk about any of these controls, as we reduce airflow, less heat is rejected from the condenser, and therefore the pressures will always rise. The reason we want to do this is because we want to maintain our evaporator pressures. We do not want our evaporator pressures to drop too low where the evaporator freezes up at a low temperature, or can just not open our TXVs and everything else, or our EPR valves may not open all the way. So we want to maintain the design pressures as much as we possibly can. Okay, so again, this is an example of the damper blades in the open position. So we have our hot gas from the compressor. In this case, we have full cooling. Okay, warm ambient temperature. Low ambient temperature, you notice the damper blades are in the closed position because of the hot gas from the compressor. The pressures are dropping. So what we want to do is increase our pressures. Condenser flooding is the final way that we can increase our condensing temperature. Flooding valves, what they do is they bypass the metering device. What we take liquid refrigerant to move from the receiver to the condenser, and that basically reduces its surface area in cold weather. Okay, it bypasses the entire liquid line metering device, evaporator, and compressor. We shove liquid refrigerant directly into the condenser and therefore reduce its efficiency. Systems with flooding valves have oversized receivers to hold excess refrigerant charge in the warmer weather. The valve is closed when outdoor temperatures are high, and all the refrigerant is directed to the condenser. By flooding the condenser with liquid refrigerant, we're basically reducing the ability of heat to be rejected. This is an example of a condenser flooding valve. You see the three-way valve that's labeled condenser flooding valve? What we're basically doing is we're saying, okay, instead of taking everything to the receiver, I'm going to take some liquid refrigerant and I'm going to push it back towards the condenser. So this is in the closed position in a warm ambient temperature, like in the summer. Now, in a cool ambient temperature, what we're basically saying is, okay, we're going to bypass the condenser. Okay. The solenoid valve is a liquid line solenoid valve or a defrost valve that's used to start or stop refrigerant flow. They come in normally open or normally closed, and they're snap acting. In other words, they're very fast, open or closed. You have to be very careful if you're installing these as replacement valves, because they have to be installed with the arrow that's printed on them in the direction of flow. Do not use them in reverse. They will not work. They're often used in conjunction with automatic pump down cycles. The valve position is controlled by a solenoid coil. Here's an example of one of these. Again, direction of refrigerant flow is very important. It's printed into the metal. You have the solenoid valve, body, and the solenoid coil. The nice part about these is if the coil goes bad, you do not have to replace the whole valve. You pop the coil off and replace the coil. If the body goes bad, you do have to recover refrigerant and braze in a new one. Okay? Be also very careful on the solenoid coil, because they do come in different voltages. Double check that coil voltage whenever you possibly can. This is a normally closed valve with the coil de-energized. You'll see that the valve is in the closed position, preventing the flow of refrigerant. A great example of this is a liquid line solenoid. When the system is pumped down, in other words, in the off cycle, the valve is closed. Now the thermostat calls for cooling. It directly sends power to the solenoid and it opens the solenoid coil. Okay, it creates a magnetic field that pulls that plunger that's in the center up. So if we look at that, that plunger's down, the black part in the center. We come back and it pulls the plunger up when it's energized. The normally open valve with the coil energized, the plunger is pushed down and the valve is in the closed position. The coil becomes de-energized. The valve is now in the open position. Pressure switches start and stop current flow to components. A low pressure switch closes on the rise in pressure. A high pressure switch opens on a rise in pressure. The low ambient control closes on a rise in pressure. The oil safety switch opens on a fall in net oil pressure. So all of these are pressure related switches. Low pressure switch can be used as a low charge position and a space temperature control. In other words, it's either a safety or a control. Low charge protection, it's set a cutout pressure that's well below normal operating pressure. The cutout pressure should be set above atmospheric pressure to prevent atmosphere or regular air from being pulled into the system. It prevents the system from operating in a vacuum. The control is normally reset automatically. If a low pressure control is applied as a thermostat, the control will cut off the compressor when the pressure equals the system pressure that corresponds to a temperature about 15 degrees cooler than the desired box temperature. Okay, so you got to look at your temperature pressure charts and you got to figure out what pressure this control needs to open at. Okay, it's at about 15 degrees cooler than the desired box temperature. The control is rated by its pressure range and current draw of the contacts. Okay, this is an example of how one's put in here. You have your T-stat, you have an overload, and you have your low pressure control. This is as a safety device. Automatic pump down system of operations, we talked about this once before. Normally closed liquid line solenoid valve is controlled by a thermostat. The thermostat opens when the desired box temperature is reached. The solenoid is de-energized and closes. The compressor continues to pump refrigerant until the suction pressure drops and then opens the low pressure control when the suction pressure drops. The low pressure control controls the compressor operation. This is an example of that. You'll notice the thermostat over on the right side under the wires closes. It allows the liquid line solenoid valve to open. When the low pressure control is closed, the compressor can become energized. The thermostat opens, closes the liquid line solenoid. The compressor is still energized until the low pressure control opens, and then everything is shut down until the thermostat next closes and releases the refrigerant back. When the box temperature rises, the thermostat closes, the liquid line solenoid is energized, and refrigerant flows to the evaporator. The compressor is off until the low side pressure increases to the cut-in point and energizes the compressor. Okay, and this is, again, thermostat's open. Thermostat closes, allows liquid refrigerant to flow through the liquid line, going through the metering line, through the evaporator, and then the low pressure control will close, and it will energize the compressor, and our cooling cycle continues until the next thermostat opens again. High pressure controls prevent the compressor from operating at a high head pressure. The control opens on a rise in pressure. It can be automatically or manually reset. It should be set up to pressure higher than the normal operating head pressure. Manual reset controls provide better equipment protection. So high pressure controls most often have a manual reset. They will not automatically reset because we want a technician to go out there and find out why the system went off on high head pressure. We do not ever want to tell a customer where these manual reset controls are, because then you'll never find out about a problem until it's too late. A low ambient fan control starts and stops the condenser fan motor in response to head pressure. Starts the condenser fan motor when the head pressure rises. Head pressure is high pressure. The setting should be lower than the set point on the high pressure control. In other words, before the high pressure control opens, I want my low ambient fan control to turn on the outdoor fan. Oil pressure safety controls are also pressure controls, but they take two readings. You find these things on larger compressors that are equipped with oil pumps. An oil pump is connected to the compressor crankshaft. Oil is forced through holes in the crankshafts. The safety control measures the net oil pressure. The net oil pressure is the pump outlet pressure minus the suction pressure. Most of these controls have a time delay built into the control to allow the oil pressure to build up as the compressor starts. Okay, defrost cycles we've already talked about a little bit, but this is just a review. A defrost cycle on a medium temperature unit, the typical box temperature ranges from 34 to 45 degrees. Coil temperatures are normally 10 to 15 degrees cooler than the box temperature. The coil will operate below 32 degrees, but the box will be above. Air in the box itself, or the cooler box, we're just talking controlled space, is used to defrost the coil on the off cycle. The coil defrosts in a random or off-cycle defrost by using the box temperature as the compressor cycles off on the thermostat. The evaporator fans continue to run while the compressor is off. The air in the box will defrost the coil. The coil defrosts a little bit whenever the compressor cycles off. Commercial refrigeration, this is the only system you will find the evaporator fans running when we're in a defrost cycle. Okay, it's because evaporator fans run all the time unless we are using electric or hot gas defrost. Planned defrost just means the defrost is controlled by a timer. The system goes into defrost at predetermined times. The defrost cycle is initiated during low load periods. Systems in retail environments like grocery stores that are not open 24 hours a day most often go into defrost when the store is closed. Okay, then we have a low temperature evaporator design. The box and coil temperatures are both below 32 degrees Fahrenheit. The coil has to be defrosted using internal or external heat. Once we have a box temperature below 32 degrees, we can no longer use the air in the space itself to defrost the evaporator coil. By internal heat, we mean hot gas from the compressor. By external heat, we mean electric strip heaters that are mounted to the evaporator coil itself. So hot gas defrost, all it means is that we're using hot gas from the compressor's discharge line. Okay, discharge gas is directed into the evaporator, and it uses a hot gas solenoid that is initiated by a timer. The defrost is terminated either by time or coil temperature. The evaporator fan is de-energized during the defrost cycle. The compressor runs during defrost, and the refrigerant condenses in the evaporator. So this is an example of how we deal with hot gas defrost. You'll see the red line that comes out of the discharge line before the condenser. Okay, and pipes to the evaporator. After the liquid line and after the metering device. It bypasses the entire condenser, liquid line, and evaporator. So in other words, hot gas is moving into the compressor, into the evaporator. Okay, so in a refrigerant mode of operation, follow the arrows. We come out of the compressor, go to our condenser, condense, then we come through our liquid line. Okay, in defrost mode, follow the arrows. Okay, instead of all the refrigerant going to the condenser, we put a whole bunch of it through the hot gas line that bypasses and sends hot gas to that evaporator. Now, if you've ever touched the discharge line of a compressor, you'll find out that that hot gas is warm enough. It's about 100 some degrees. It will melt the ice relatively fast off that evaporator coil. External heat defrost is known as most often as electric defrost. Okay, I just want you to have both terms because you'll see it sometimes both ways. It's usually accomplished with electric heaters mounted to the evaporator coil. Defrost is initiated by a timer. The defrost temper is terminated, in other words, shut off and sent back to cooling by either time or coil temperatures. The evaporator fan is de-energized during defrost, and the compressor is turned off during the defrost cycle if you're using electric defrost. Now, when we talk about time or temperature, we are going to be using a defrost termination and fan delay control. It's a single pole, double throw switch. It terminates the defrost when all the frost has been removed based on coil temperature. It delays the evaporator fan start until the coil temperature drops. We know that when ice has been removed, the evaporator surface temperature increases. The control senses this increase in temperature, and the system is put back into the refrigeration mode mechanically. When the coil temperature drops to the set point, the fan is energized. This is an example of actually a defrost termination and fan delay control. It's a single pole double throw switch. You have to know which wire goes to where. If you get these backwards, you can actually burn out a defrost time clock. Okay, so again, always look at the label. They're always color coded, but different manufacturers will have the colors in different orders. Oh, one other thing. This is all on the neutral line. in most cases. You'll see this connected either to L2 or neutral. It disables the neutral side of the fan, of the evaporator fan, and it connects to the neutral side of the X terminal on the defrost clock. That's the little solenoid that's in the defrost clocks. Receivers are found in most refrigeration systems, especially those that are low temperature or pump down. They're located in the liquid line. The device stores liquid refrigerant, and refrigerant leaves the receiver as 100% liquid. It's very important that that refrigerant goes into TXVs and EEVs as a fully liquid. You cannot have any vapor in those. Now, they're not found in critically charged or capillary tube systems because those are very specific set for flow, and it's a critically charged. They are found on systems with automatic or thermostatic expansion valves. Okay, if you take a look at this image, you'll see the liquid line from the condenser comes into the receiver. The refrigerant falls to the bottom of the receiver, and a dip tube that pulls from the bottom of the tank ensures that only 100% liquid is flowing to the metering device. The King valve on the receiver is located in the liquid line between the receiver and the expansion device. Under normal condition, this three-way valve is back-seated. The valve can be front-seated in order to pump the system down. It has a service port that enables the technician to take pressures when the system is running. The valve must be cracked off the back seat to take pressure readings. In other words, we have three positions. We have back-seated, which is normal operation. We have mid-seated, which allows the service port to be open. And we have front-seated, which allows the system to be pumped down. Okay. So again, here's the example of the King valve or liquid line service valve. And if you look at this picture, you can see what we're talking about having three positions. We have the service port, we have the device port, and we have the liquid port. In this picture, the valve is back-seated. You'll see that it is actually blocking the service port. So you can put your gauges on, you can take them off, and you won't have any refrigerant loss. That's the back-seated position. Service port is sealed, line port open to the device port, because you see right here, liquid refrigerant can move through here. This is your normal operating position. Cracked off the back seat position, or we call it mid-seated. The service port is open, the line port is open, and the device port is open. It's the position used for taking system pressure readings. It's also the position used for adding or removing system refrigeration, is mid-seated. Okay. Front-seated position. The service port is open to the device port. The line port is sealed off. You see that it is all the way in. It's the position used for pumping the system down. In other words, if you need to trap your refrigerant, okay, from in one location, you can actually front seat it, and you can use this to be able to change out parts on the low side of the system. Filter dryers you see in most refrigeration systems. They're located in the liquid line. The purpose of the filter dryer is to remove dirt, moisture, and acid from the refrigeration system. It includes a decadent, that's activated aluminum or molecular sieve and silica gel. They can be permanent or replaceable core types. They're connected to the system with either solder joints or flare connections. Okay, refrigerant check valves are sometimes found if you have a very high roof or a large drop in refrigerant. It allows refrigerant to flow in one direction only. They can either be ball type or magnetic type. They must be installed with the arrow pointing in the direction of refrigerant flow. They're installed at the outlet of the lowest temperature coil on multiple evaporator systems. Sight glasses are becoming less and less frequent, but you still see them. They're installed in the liquid line. It enables the technician to determine if a solid column of liquid is reaching the expansion device. They also more usefully have a moisture indicator. They're usually installed after the filter dryer. It used to be people used to look for bubbles in the sight glass. That is no longer the case. Bubbles in a sight glass do not mean anything anymore. Liquid refrigerant distributors are used on multiple circuit evaporators. They're located at the outlet of the expansion device, and they're designed to allow equal refrigerant flow to all evaporator circuits. Some distributors are made with side inlets, which are used for hot gas defrost. Sometimes you'll find, especially on newer systems, that there are now heat exchangers installed. You'll see these very often in restaurant, hotel, or supermarket refrigeration systems. Okay, they're installed in the suction line leaving the evaporator. Suction and liquid gases lines are connected to allow heat to transfer between them. This increases the amount of subcooling in the liquid entering the expansion device. It prevents liquid from moving through the suction line into the compressor. So this is just an example of a cap tube system. Now this is probably out of like a drinking fountain or something like that. But all it does is allow the lines to connect, usually with solder or braze, to allow heat exchange. Okay. This is just an example of how this works. The high temperature, high pressure refrigerant line in the cap tube transfers the heat from the cap tube to the refrigerant in the suction line, which just increases subcooling as well as superheat. Makes the system slightly more effective. Suction line accumulators are located in a suction line close to the compressor. All these do is prevent liquid refrigerant from entering the compressor. It gives liquid a place to boil off before entering the compressor. Sometimes liquid line is routed through the accumulator to help boil away any liquid and also increase subcooling. We want to make sure that even in low temperature operations, we do not have liquid refrigerant getting back to the compressor. The other place where you find these suction line accumulators is in heat pump systems. Okay, when you're dealing with heat pumps in air conditioning and heating. But we want to make sure we never have liquid refrigerant coming back to the compressor. So all this does is give a little bit of extra to the suction line and to the superheat process. This is an example of, again, an accumulator. The suction gas goes to the compressor, but from the evaporator comes into the accumulator shell. Okay, you notice the U in the suction line coming out of the accumulator shell. Okay, it's designed to pull the gas from the top of the unit rather than the liquid from the bottom of the shell. So we only want gas going back to the compressor. Okay, sometimes again we can route the liquid line through these things. Okay, to provide a little bit more heating of any liquid refrigerant that might be found in there. This is not that frequent. So we want to be very careful of liquid flood back to the compressor. There's a couple reasons you need to know about for liquid flood back. We have improper TXV setting. In other words, the TXV is too far open and is allowing too much liquid refrigerant into the evaporator and it's not boiling off. It's pulling back to the compressor. We have an oversized TXV. In other words, someone put in the wrong TXV and has its sides too big for the evaporator. Again, allowing too much liquid refrigerant through the system. We might have a loose TXV or thermal bulb. Okay, it's not sensing the proper temperature of the discharge of the suction line coming out of the evaporator. It's allowing the system to be too far open. We might have a system overcharge. Too much refrigerant in the system is not boiling off before it reaches the compressor. We might have a restriction in the airflow through the evaporator coil. Again, reducing the refrigerant from being boiled off and allowing liquid refrigerant back to the evaporator coil. We might also have a low system load. Okay, or defrost problems. Too much ice on the evaporator, which is preventing the liquid refrigerant from boiling off. Sometimes we have liquid line filter dryers. They're located in the suction line. Okay, good. It provides some additional compressor protection, and it must be installed when any system has become contaminated. Anytime a system has acid in it, we want to install a suction line filter dryer. These usually have two pressure ports to read the pressure drop across the device. Most often, if you have a filter dryer in any system, you do not want to have a pressure drop. A pressure drop across a filter dryer means that the filter dryer is starting to get clogged. Okay, we have suction service valves. They're the same as the liquid line or the king valve. They're normally attached to the compressor. Back-seated is normal operation. Front-seated is used for pump down and service. Mid-seated is used for system evacuation. Okay, and also to take pressure readings for charging or for any time you need the service port. So again, service valves, back-seated, normal position. Mid-seated, we can use the service port. Front-seated, we're pumping down. Discharge service valves are located in the discharge line. They're normally attached to the compressor. They can be used as a gauge port or to valve off the compressor for service. They use the same positions as the suction service valves. Do not ever front seat a discharge service valve when the compressor is running. Okay, if you front seat the service valve with the compressor running, the discharge service valve, you'll blow up the compressor. There's no place for that refrigerant to go, and it will start blowing out the valves and bearings in the compressor. On a lot of the larger systems, you'll see oil separators. They're installed in the discharge line. What it does is separates the oil from the refrigerant and returns the oil directly to the compressor. Oil drops and falls to the bottom of the separator. The oil level raises a float and opens a valve. The difference between the high and the low side pushes the refrigerant back or the oil back to the compressor. Oil separators have to be kept warm. If they're not kept warm, liquid refrigerant will start accumulating in them. This is an example of an oil separator. We have our discharge from the compressor that comes in, okay, fills this space with a combination of oil and refrigerant because that's what carries our oil. The oil particles fall to the bottom, okay, because they're heavy. The discharge line to the condenser takes my pure refrigerant gas with no oil. As the oil starts rising in here, okay, it opens a float valve. When the float valve opens, it's going to allow that oil to be sucked out of the oil separator and back to the suction line of the compressor. So the pressure difference between my high discharge pressures and my suction line of the compressor is going to pull that oil back into the compressor. Pressure access points are sometimes installed to take readings at various points in the systems. Some people have installed line piercing valves, can be installed when the system is running. They can be saddle type or solder type. They have a small Schrader pin or a small valve. Okay, crankcase heaters prevent the refrigerant from migrating to the oil in the off cycle. Prevents oil from foaming and being pumped out of the compressor. They're external type, most often, in other words, they're wrapped around the base of the compressor, or some of them are actually inserted into a cavity in the compressor shell. Crankcase is needed during off cycle and is sometimes controlled by a set of normally closed contacts that open when the compressor is energized. If you look at a contactor in some of the bigger systems, you'll see that it's an extra connection on the back of the contactor itself. It's normally closed. That's why you always check with a voltmeter to see what is energized, even if the compressor is not running. So all of these that we've talked about are additional components that you may or may not find on the average refrigeration system. Okay, you have your four basic components and then you just build from there.